Greetings and welcome to Chapter 5, Lesson 5.2, the Uniform Distribution. Get to know the new terminology for this lesson. Click on each of the words, learn its definition and meaning. When you are ready, click Continue. In our previous lesson, we really did work with the uniform distribution. Now we're giving it a name. So here are some characteristics about the uniform distribution. 1, events are just as likely to occur. They're equally likely to occur. Our data could be inclusive or exclusive of the endpoints, depending on how our values are given to us. Our notation is going to be this x tilde u, where we have a and b. A is the lowest value that x can be. B is the highest value x can be. The probability density function is a calculation. It's always going to be f of x equals 1 over b minus a. And remember, x is between a to b. If it is inclusive, it's going to be a is less than or equal to x is less than or equal to b. If a and b are not included, then it's going to be a is less than x is less than b. Now, it really kind of doesn't matter if we include a and b in the terms of calculating our probability. Calculating probability is different than the curve, the function, the probability density function is the line we're creating in the uniform distribution. Everything inside the shape, that rectangle shape, are our probabilities. And if we include the endpoints or exclude the endpoints, it doesn't change the amount of the probabilities. It would change what we include in the actual function itself, just not in the probabilities. Because if you remember from last lesson that the area under a specific value is 0. So including them isn't going to add to go over our 1 that our probabilities can be. Our area isn't going to grow just because we have these values included or not, because the area specifically under a particular value is 0. Our formulas for the mean and the standard deviation, mean, well, it's just the average of the high and low. So a plus b all over 2. Our standard deviation is going to be the square root of b minus a all squared divided by 12. Now, lots of students ask me, well, why is it divided by 12? And there is a big, long explanation for that. And in essence, just go with it. Just go with the flow. It is divided by 12, and then you take the square root of all of it. If you really want to know why, I will tell you. Just reach out to me and I'll let you know why it's divided by 12. Otherwise, just go with the flow. There's nothing like just diving right in. So let's hit up a problem and just work it to pieces with everything that we need to be able to do for a uniform distribution. Here's our problem description. ACE Heating and Cooling Services finds that the amount of time a repairman needs to fix a furnace is uniformly distributed between 1.5 and 4 hours. Let's let X be the time needed to fix a furnace. Well, then we're going to say that our X is uniformly distributed between our low value of 1.5 and our high value of 4. So just in that little statement, it tells us all the math that we need to know. The problem description tells us the nice little story that it's ACE Heating and Cooling and furnace repairman and all of that. But just the U, parentheses, 1.5, comma 4, end parentheses, tells us everything we need to know mathematically. Let's find the mean, the standard deviation, and the probability density function, which is f of x. Our mean is just going to be our high value plus our low value, or our low value plus our high value, all divided by 2. So our low value, 1.5, plus our high value of 4, all divided by 2, throw that into a calculator and you get 2.75. So the average amount of time it takes a repairman to fix a furnace is 2.75 hours, or 2 hours, 45 minutes. Our standard deviation is the square root of b minus a all squared divided by 12. So we're going to take our high value, 4, minus our low value of 1.5, and square it. We get 6.25 all divided by 12. And if we square root that, we get, and this is pretty much a calculator problem. You can throw it all in, all at one fell swoop to most calculators. Just be careful of your parentheses. 0.7217 is our standard deviation. Now let's find our probability density function, f of x. Now our probability density function is 1 over b minus a. And this is for our high value through our low value. Our low value is less than or equal to x is less than or equal to b. So our high value is 4. Our low value is 1.5. So our f of x is going to be 1 over 4 minus 1.5. And you throw that into a calculator, you get 0.4. So our f of x equals 0.4, or you can think of this as 2 over 5, 2/5, but it's easier to work with the decimal, so I'm going to go ahead and leave it as a decimal. So we do state it as f of x equals 0.4 for the values of 1.5 is less than or equal to x is less than or equal to 4. We do need to know what our boundaries are for x. What does our f of x and our graph look like? I mean, this is a quote-unquote curve. Granted, it's a straight line, but our high value is 4, our low value is 1.5, and our curve is always 0.4. So in essence, uniform distribution looks like a rectangle. And if we add up all the probabilities in the shaded region, those are going to add up to 1. Now that we know what our full distribution looks like, let's find the probability that a randomly selected furnace repair requires more than 2 hours. So because we have a boundary at the top of 4 hours, our more than 2 hours must be between 2 and 4. So our probability of 2 is less than x is less than 4. Again, you can use less than or equal to. It's not going to change anything. Our probability, because it's a rectangle, is going to be base times height. Now, if we look at our graph, we can see where our shaded area is. We're missing a little bit of the full function between 1.5 and 2, but the rest of it is shaded. We need to calculate the base of our rectangle, the height of our rectangle, multiply the two of them together, because base times height, or length times width, is the area of our rectangle, which is our probability. So our base, our high value is 4, our low value is 2, so our base is of length 2. Our height is what our function is, which is 0.4. When we multiply these two together, this is what our probability is going to be. 2 times 0.4 is 0.8. So the probability that it takes more than 2 hours, in other words, 2 is less than x is less than 4, is 0.8 or 0.80. In other words, 80% of the time, it's going to take 2 or more hours. Here's a new scenario. Let's find the probability that randomly selected furnace repair requires less than 3 hours. Now, our bottom boundary is 1.5, not 0. Remember, our x values go from 1.5 to 4, but we only want to know less than 3 hours. So our minimum is 1.5, our maximum now is 3 hours. So the probability that 1.5 is less than x is less than 3 is going to be our base times our height. Our base is 3 minus 1.5, in other words, 1.5. Our height is still our f of x, which is 0.4. So the probability that 1.5 is less than x is less than 3 is 1.5 times 0.4, or 0.6. You can think of this as the probability that it's going to require less than 3 hours is going to be about 60% of the time. Now let's find the 30th percentile of furnace repair times, meaning how many hours would constitute 30% of the probabilities. Now, I think that it's always better to kind of sketch a graph of what you're trying to solve to kind of make it make sense. So I know my shaded region is going to be 0.3. That's my probability of the 30th percentile is 0.30. I'm looking for somewhere between 1.5 and some value. That shaded region equals 0.3. So I know my end result. I'm going to have to kind of work backwards to figure out my unknown value. I know my low is 1.5 because it has to be. That's the low value of my x. My high value, I don't know. I'm just going to call that k. And I know that the height is still 0.4. So I'm going to kind of put this all together now. My base is k minus 1.5. That's the length. I don't know what k is. It could be 2. It could be 3. I don't know. My height is 0.4. I know if I multiply these two things together, they are going to equal the 0.3 probability. So k minus 1.5 times the 0.4 equals 0.3. From here, it's an algebra problem that I'm solving for k. 0.4k minus 0.6 equals 0.3. Add 0.6 to each side and I get 0.4k equals 0.9. Divide both sides by 0.4 and I get k equals 2.25. Therefore, the 30th percentile would be 2.25 hours. Let's do one more problem with this information, this problem description. The longest 25% of furnace repairs takes at least how long? Now again, I like to draw a little graph of what the problem looks like. So I'm looking for the top 25%. That means I'm bounded by my high value of 4, but I don't know what that low value is. I'm going to call that k. So what I'm really looking for is the probability that k is less than x is less than 4 equals this 0.25 probability. We've got to figure out our base. We've got to figure out our height. Our base is going to be our high value minus our low value. So 4 minus k is our base. Our height hasn't changed. Our height is still 0.4. Let's multiply our base and height together. 4 minus k times 0.4 is going to equal the probability we're looking for of 0.25. Distribute through, we get 1.6 minus 0.4k equals 0.25. Subtract 1.6 from both sides, we get 0, negative 0.4k equals negative 1.35. And divide both sides by negative 0.4, we get k equals 3.375. So 25% of furnace repairs take at least 3.375 hours to complete. You are trying to always make sense of the values that you're getting. If that value was something like negative 0.2, my math is wrong because the hours of time that it takes can't be negative. So be mindful about what your answers are and if your answers make sense. Try and put them in terms of the problem and see if it does make sense. Let's go through a full walkthrough of a problem given some data. The cool part about uniform distribution is we really just need our high value and our low value. So here we have 55 data points of smiling times for 8-week-old baby. And they range from a very low value of, I'm trying to find the lowest one in here, it looks like 0.7, all the way up to, there's a 22.8, 22.8. Looks like 22.8 is our largest value. So if I was to kind of round these off to integers, let's say these are uniform distributions from 0 to 23. So our x values, 0 is less than or equal to x is less than or equal to 23. Okay, now that we know what our x values can be from 0 to 23, let's go ahead and first calculate the mean and standard deviation. Our mean is going to be our low value plus our high value all divided by 2. We're just looking for the average between our low and high value. 0 plus 23 all divided by 2 turns out to be 11.5. Pretty straightforward calculation. For our standard deviation, it's going to be the square root of our high minus low all squared divided by 12. And throwing that into a calculator, we get a standard deviation of about 6.64. Now, from here on out, besides knowing what our mean is and knowing our standard deviation, we're really not going to need to use those values for any of our probabilities. What we're going to need to find out is our f of x, our probability density function. That's always going to be our height of our uniform distribution. And then we're going to have to find our base for any probabilities that we calculate from here on out. Let's find that probability density function. We want 1 over our high value minus our low value. Our high value is 23, our low value is 0, so it's going to be 1 over 23 minus 0, 1 over 23. So that is our probability density function. If you want to turn it into a decimal, you can. It doesn't matter with your calculations. Ultimately, you're going to throw it into a calculator. So I'm fine with it being 1 over 23. What is the probability that if we randomly chosen an 8-week-old baby that it smiles between 2 and 18 seconds? All right, it's always helpful to sketch what you're looking for. So our probability function is at 1/23, and our range of values go from 0 to 23, and we're looking for that range between 2 and 18. So just the probability in the shaded region is what we're looking for. We need to find the length of our rectangle, our high value minus our low value of the probabilities we're looking for. So 18 minus 2 is 16. 16 times 1/23 is 16 23rds. In other words, 0.6957. Like I said, fairly straightforward when we're dealing with a shape like a rectangle. Length times width, or in this case, base times our height. So the probability that if we choose a baby at random, they will smile between 2 and 18 seconds is about 69.57%, 0.6957. Let's find the 90th percentile for an 8-week-old baby's smiling time. So in this case, we have our probability, our percentile, 90 or 0.90, but we don't know our x value. We're looking for that. Again, just kind of wanted to sketch my graph to see what it's going to look like. I'm going to go from 0 to some value. I'll just call that k. And that probability will equal 0.90. So I know the length of my rectangle times my height of my rectangle will equal the 0.90. So k minus 0 times 1/23 equals 0.90. K over 23 equals 0.90. Let's multiply 23 to both sides, and we get k is 20.7, meaning the 90th percentile of an 8-week-old baby's smiling time is 20.7 seconds long. That's a long smile, even for an adult. My goodness. Let's change up the problem a little bit. Let's find the probability that a random 8-week-old baby smiles more than 12 seconds, knowing that the baby smiles more than 8 seconds. We know the baby already smiles more than 8 seconds. So what's the probability that the baby actually smiles more than 12 seconds? There's 2 ways to calculate this problem. The first option is to actually create a new probability density function. Instead of going from 0 to 23, we know we go from 8 to 23. We already know the baby smiles more than 8 seconds. So our new probability density function is our new high minus our new low. So 1 over 23 minus 8, in other words, 1/15. This is our new fx. The rest of the process is exactly the same. So now we want to know more than 12 seconds. That's going to be from 12 seconds to 23 seconds. So the probability that 12 is less than x is less than 23. The length of our rectangle is going to be 23 minus 12, all times our new probability density function of 1/15. It was adjusted for the new information of more than 8 seconds. That's 11/15 or 0.7333. That's one way of dealing with hey, the baby smiles 12 seconds given the baby already smiles 8 seconds. This is a given problem. 12 given 8. The second way of calculating this is the probability of A given B, using that formula that we've used in the past. So the probability that x is greater than 12 given x is already greater than 8 is the calculation of the probability that x is greater than 12 and x is greater than 8, all divided by the probability that x is greater than 8. Now, if we calculate the x is greater than 12, because it has to be true in both places, so it's not going to be this little area from 8 to 12. They've both got to be true, so the probability has to be x is greater than 12 on top. And then the probability is x is greater than 8. The probability that x is greater than 12, well, 23 minus 12 is 11 out of those 23. Probability that x is greater than 8, that's going to be 23 minus 8 over 23. So we have 11/15 is 0.7333. Personally, I like the first option. It's less confusing. Just readjust our f of x and then treat it like a normal problem versus, oh gosh, which combination do I have to do? This and this divided by this. And I think it's complex, the second option versus the first option. But you may do it either way. They both get you the same answer.